Welcome back, everybody. Today is the third session of the Gridlab-D developer training. Today's topic is going to be Gridlab-D modeling. So we'll be focusing on the language and the models that Gridlab-D can simulate with. So I'm going to get right into it. There are really two parts to understanding how to model in Gridlab-D. The first is the modeling language itself that is used to construct models using a fairly straightforward syntax. And the other is the JSON representation of models. That's a fairly standard file format that's used for interchange between software. The GLM format is really designed to allow us to model multiple domains simultaneously in a single language. And so we're going to be talking about not only the syntax of the language, but some of the semantics itself. Obviously, since this language is really designed specifically for Gridlab-D itself, it's not a very portable language. And of course, the syntax changes over time. Which is in contrast to the way JSON works, which has a very simple syntax, but as a result, the semantics are more complex. The advantage of JSON, of course, is that the file format that is used to represent the Gridlab-D models is much more portable, and the syntax is much more stable, which means that programs that want to read and write JSON files will have a much easier time of it. The flip side, of course, is that because the semantics of the content is more complex, it means that we need an API, programming language interface to allow us to work with JSON files over the long term. We're not going to talk about the API today. We're just going to focus primarily on the Gridlab-D modeling language itself and the format of the JSON file. When we talk about converters, we'll talk about the JSON API a little bit more extensively. So today's discussion on JSON is going to be pretty limited. So let's just jump right into the Gridlab-D modeling syntax. The language itself is a text-based file. These files essentially contain a bunch of directives that help Gridlab-D construct a model according to your specifications. These directives are fairly easy to read. So they're really designed for people to be able to enter in the information that they want and assemble all the components of the model needed to describe a multi-domain simulation. There are also macros which are used to manipulate how the GLM syntax is interpreted based on conditions. And do things like control the flow of the loader as it reads the GLM files, and perhaps generate output and other such things that might be necessary as you go along. And then we'll talk a little bit about some general semantic questions related to the GLM files themselves, how global variables work, and how object properties are defined. There's quite a lot of capability in the Gridlab-D modeling language that most people, even experts in Gridlab-D, don't typically know about or don't use very often. And we'll try to cover all of these more esoteric points in today's session. So let me just start with probably the most important directive in a Gridlab-D simulation, which is the directive that controls how time is handled during a simulation run. The clock directive is used to set the time zone and the start and end time of a simulation. Almost all models need to have this. If you don't include this in the simulation, as a general rule, you'll get a one-time solution to the model if the model is able to settle into steady state. And if it's not able to settle into steady state, you'll get an infinite running simulation. When I say infinite, it runs for, I believe, 1,000 years if you start it at the default time and run to the default end. Obviously, that's not very useful, but the simulation essentially will run until it either reaches the stop time that you specify, or it reaches steady state, meaning that there's no further changes pending in the simulation. When you specify time zone, there are a couple different ways you can specify it. You can just specify it using the standard POSIX definition that is used by a lot of operating systems, which is, what is the standard time representation? What's the offset with respect to universal time? And then what is weather, and what is the daylight savings time specification? Alternatively, though, you can also specify it in terms of country, region, and city, or continent and city. So these are two different specifications that are also supported for determining the time zone. Otherwise, the start and stop times are always defined in the ISO format, so year, month, day, hour, minute, second, and time zone according to the time zone specification, the POSIX time zone specification. So this is pretty straightforward, but as I said, almost all models need these specifications in order to know when to start and when to stop, because otherwise the default start time is January 1st, 2000 midnight local time, and the default stop time is, steady state or 1,000 years hence. So that's basically it for the clock directive. There's really not much else that we could do with this. All of these values here are also available as global variables. And so you can always inspect using global variables what they are and use them for other purposes if necessary. The next most important directive is the module directive. And what this directive does is it loads all the classes associated with a particular module. And modules are generally associated with a domain. So in this case, this example, first one is the residential module, which is associated with modeling residential buildings and a house in particular, and all of the associated classes of objects that you might find in a house, such as appliances and so on. The second example is the power flow module. And so this module loads all of the classes associated with electrical modeling an electrical system, and the support infrastructure needed to solve power flow within an electrical system. And so in this case, we see an instance of a module global variable being used to tell the module what kind of solver it should use. And in this case, it's specifying what's called the forward back sweep method, which is a way of solving a radial network model that's quite efficient. Some alternatives might be the Newton-Raphson solver, which is a more general solver that can be used for solving mesh networks. And so the ability to set local variables is what you use to tell the module what features you want enabled and how you want the module to work. And so we will see as we go through examples later of different modules being used, we'll see instances where we set these values in order to make it do something in a particular manner, as opposed to what it would do by default. So these variables, like this solver method variable, are stored as global variables where the module name is prepended to it. So it's the prefix with a double colon separating the module name from the name of the global variable. And so we'll see this later on in situations where we want to access a particular global variable that belongs to a module. This will be how we would refer to it. Some modules do change this GLM syntax. It's pretty unusual, but it is possible for a module to alter the way GLM files are interpreted. I can't think of any common ones that do this off the top of my head, but it is allowed. It's just not used very frequently. Next is the class directive. And this directive really can do three important things. First of all, it can define a new class. So if you just define a class called test and it's not already defined, then it will create that class and it will create all the properties that you want, that you list in that class. Notice that for some properties, you can specify the units. Doubles and complex values can have units. Other properties cannot, but they may have other features such as enumerations and sets having keywords, for example. And that syntax for different properties declaration is documented in the Gridlab-D documentation. But it's a pretty straightforward way of creating your own class that implements a bunch of properties, and then we'll talk about later how you implement methods in those classes. The other way that it can work is if the class already exists, then adding a declaration to that class would simply add another property. So declaring, if the class test already existed, then this declaration would simply add the T property with a unit of seconds to the existing test class. Finally, the other thing that it can do is if the class exists and the property already exists, then what this does is it verifies that the property conforms to the specification that you're giving. So in this case, because the class already exists and the property exists, P, this is going to check whether this new declaration of P is compatible with the old one. Which from the perspective of the units, it is compatible. VAs are compatible with watts, but from the perspective of the data type, it is not compatible. And so this declaration would fail to pass because the verification of the data type would not be successful. So this is a convenient way to ensure that the units you intend to use are compatible, and the units and the data type that you intend to use for a property are compatible with the way it's already been declared. And this, if you are doing something where the data type or the units are important, the result is sensitive to them, then this kind of verification may be useful. Here's a list of all the different property types that are allowed in a class declaration. So Booleans, bool is used for declaring a Boolean true-false value. These are different fixed length character strings. So these essentially strings that have a limited length and otherwise can represent any arbitrary text. Integers of different sizes, including timestamps, which are essentially 64-bit integers, optionally with an additional 64 bits to specify the fractional portions of the seconds, nanoseconds. But generally timestamps are seconds and up, counting from January 1st, 1970, I believe. So timestamps are essentially the seconds of what is called the Unix epoch. Enumerations and sets allow you to use symbols as representations for different values. In enumeration, the symbols are mutually exclusive. It can be either A or B or C. And in a set, they can be combined, so you can have A and B, or A and C, or B and C, and so on. Doubles, complex, floats, reals, random vars are all essentially an underlying double. In the case of complex, the real part is the underlying double. The interesting feature about random var is that the value can change over time following a random distribution, which is a useful way of introducing noise into a simulation, or having a value that follows a particular distribution for testing purposes. Load shapes and end uses are also underlying doubles. In the case of a load shape, it's driven by an arbitrary value that changes over time following a schedule. And in the case of an end use, it's a load shape that has a particular behavior associated with an end use, like lighting or plugs or something like that. There are also some other properties that are available, but they haven't been used enough for us to be confident that they work in all the circumstances that we think they might be useful. String is an arbitrary length string. Python is a Python object, which allows you basically to capture the properties of a Python object itself in the Gridlab-D model and share it between other Python code, so that you can have, for example, one object contain some data that was generated by Python and pass it to another object and have that other object manipulate that Python data. A double array is simply an array of doubles that you can index. It's two-dimensional, and the same with complex arrays. Next is the object directive. So the syntax of the object directive essentially is to take a class and instantiate it by assigning some of its proper or all of its properties particular values. Objects always have some header values such as name or parent, and we'll talk about all the different header values later. So you don't need to declare those in order to be able to use them. They always come with an object because they're used for managing objects globally throughout the simulation. Typically, if you declare an object and you give it a name, then you can refer back to it from another object and create a hierarchy of objects. This becomes particularly useful when using solvers that where the sequence of updates through the objects is important, which is most solvers. Certainly the PowerFlow solver is very sensitive to that. Another way of creating the object hierarchy is to simply embed one object within another. And this avoids you having to assign the parent object a name because instead the embedding happens implicitly and is captured without using names. But otherwise the effect is largely the same. Okay, so here are some examples of properties that you can assign to an object. So the first property here is enabled as a Boolean value, so you can either assign it true or false. Motor state is an enumeration in the residential house object, and it has a number of states, including one called stalled. It has another probably, I think, called running. Here's a set where the options are a combination of two flags, flag 1 and flag 2. The two are both set. The vertical bar is used to separate the keywords. If all the keywords of a particular set are single letter keywords, then you don't need to put the vertical bars. You can just list the letters explicitly. And so, for example, the phases property of PowerFlow objects are all one lettered. And so you can have phase A, phase B, phase C, and delta configuration simply by saying A, B, C, D. Strings are simply set by providing the string value. Dates are set by providing the date string itself. You can provide a number, which would be interpreted as the seconds since 1970. And so that's allowed. That allows you to set values very efficiently because the internal way in which dates are stored is actually as the seconds since 1970. And so it avoids parsing the value and just passes around the seconds since the start of the epoch. Here's a double value floor area, which can be set either by providing the number, assuming you know what the units are and you are using the same units. If you're uncertain what the units are, or you want to be absolutely certain that the value you're providing is converted correctly, you simply provide the units. And so here, setting the floor area to 250 square meters allows you to be certain that you're getting the right area, particularly because you may not be certain what the floor area is stored as internally, and providing 250 might not work. And in fact, it wouldn't work the way you expect because usually floor area in the house module in particular is stored in square feet. And so providing the unit ensures automatic unit conversion and correct handling of the value that you provided. Another way of setting a double is to use a distribution, sampling a distribution. Now, in this case, this is what's called a functional, and we'll talk more about functionals in a bit. But what happens is that the value that is obtained by sampling this triangular distribution is set directly into the floor area itself at initialization. And it's never changed after that. So it gives you a way of initializing a particular property using a random distribution without having it change later, as we'll see with the random var property. So this is good for doubles and complex values. It allows you to set them and initialize them with some randomization and then leave them alone from then on. Another way of setting a value is to have a calculation based on another value. So in this case, the wall area here is set to the square root of some variable, which was presumably set elsewhere in the object, times 8. So it's just taking the floor area, multiplying the square root of that particular value and multiplying it by 8. Presumably that value might be, something that would be related to the square root of the wall area. So this is just an example of a math calculation. So notice that they're done in parentheses. So anytime you find a property that's in parentheses, it will interpret it as needing a math calculation using the standard math library. We will talk more about expansions later, but notice the backtick here on each side of it, which forces the loader to interpret this as requiring delayed evaluation of the properties that are in the curly braces. And when I say delayed, we'll see later as we talk about looping and control mechanisms in the GLM file, because variables are expanded with a $ immediately as they are read. That might not work as you expect if you have a loop, because that variable would be expanded before the loop is put together, and the backtick will delay it until after the loop is put together. And so here's an example of an expression, which is taking the value of a variable and then performing some operation. Here it's a post increment. And then finally, what are called ternary tests, where the value is, the property is evaluated, and what's in the parentheses, if it turns out to be non-zero, so it should be a double or complex, but if its underlying double is non-zero, then the first value is used, and if it's a 0, the second value is used. And so ternary operators are how you get alternatives implemented depending on another value in an object. So some general rules for values. If the string has any kind of special character, and spaces in particular, you should use quotes to avoid interpreting those characters. Semicolons, commas, spaces can all result in parsing errors if you don't put string double quotes around a string. You can use triple quotes, so 3 double quotes in a row, if you want to keep the new lines as well. This is really useful for very long values or values that actually have new lines in them, and you want to preserve the literal text. There are cases where this is highly desirable. It's not used very often, but it is supported. As I said, functionals are allowed, and they can be used outside the parentheses of math, and it will still return a math operation. Right now, the only types of functionals that are used are random number generators. There are no other functionals that I'm aware of implemented in the loader's library. And then some properties use an extended syntax that looks kind of like JSON syntax. And so here's an example of a random var property that uses this kind of extended syntax to set the type of the random variable, the minimum value, and how often it's updated. We'll talk about that a little bit more. But it is not unusual to find some properties that use extended syntax. The properties that have units, so as I said earlier, they can do automatic unit conversion. Double and complex values have units associated with them. It's not required. So if a property does not have a unit, then it's assumed to be unitless, and attempting to use a unit won't work. But if the property is assigned a unit, then any value you give it without units will be assumed to be in those units. And if you give it a value in another unit, it must be a compatible unit. So for example, watts can be converted to megawatts automatically by doing scaling. And if you, for example, were to put megawatt hours as the unit, you could then convert VA hours, and that would work correctly. The system also understands derived units. So for example, you could use V times A times H to automatically convert to megawatt hours. And that would work correctly. So here's an example of a derived unit that's megawatts per hour, and objects are allowed to have derived units, and those will work just fine. The complete list of units are given in a unit file in the runtime folder called unitfile.txt. And it's quite a comprehensive file, and it's perfectly okay to add additional units to that file as long as they're correct and not conflicting with anything else. You should be careful when adding units not to create ambiguous units, given the fact that there are some units that have prefixes for the various scales like K, M, C, and so on. So some of those may actually already be effectively in existence, even if you don't see them listed, just by virtue of the fact that the system understands the scalars. And then finally, if you do not, final important reminder, if you do not specify the unit when you provide a value, the property's current unit is assumed. My suggestion, and I try to make a habit out of this whenever I do modeling, is to always put the unit so that I can be absolutely certain that the value that I'm providing has both compatible units and that the scaling is done correctly. It's not unusual to find that the values used in one module have one scale, and values for the same kind of property in another module use a different scale. And so using the unit conversion is a good idea to ensure that values get converted properly when they move between modules or when they're coming in from external applications through converters. All right, so now we're going to get into some of the little bit more interesting and esoteric parts of the Gridlab-D modeling language. The first one is the filter directive. This is used to implement a Z-domain filter. Think of it as a transfer function defined in Z-domain, so in a discrete time specification for a transfer function. You can implement all sorts of things. There are, of course, some pretty typical ones like delay and finite difference filters. Here's an example of a delay filter that simply implements a delay of 10 seconds. And so when a property refers to another property's value through a delay filter, it sees the value of the other property 10 seconds after it changes. Here's another example of a delay with additional specifications. And in this case, it includes a low resolution specification, an 8-bit value, meaning that the filter is going through something akin to an 8-bit analog to digital converter. And it also has minimum and maximum thresholds. So any value above 2.5 or below 2.5 would be clipped at that value. And so these kinds of specifications allow you to implement a lot of the kinds of things that you find in digital systems, digital control systems in particular, and allow you to implement things like saturation and low resolution digital systems. Another important feature of filters is that they are additive. So here's an example of 4 different filters that allow you to implement essentially a 2-input, 2-output transfer function. So notice here that filter 1.1 takes input 1 and sends it to output 1. Filter 2.1 takes input 2 and sends it to output 1. So notice that it adds it to output 1. And then similarly, filter 1.2 takes input 1 and sends it to output 2. And filter 2.2 takes input 2, filters it, and sends that to, adds it to output 2. So you can essentially create not only single input, single output filters, but using this mechanism, you can create multiple input, multiple output filters of just about any complexity you want. So once you've got these filters specified in Z-domain, the simulator can implement them as necessary. And so this is a very important feature. It's not, I haven't seen it used a lot, but for those who want to develop much more complex transfer functions that connect objects together. This is a very general mechanism for doing so. For those of you who are interested in the subject, there is right now no implementation of a S domain, a continuous time filter. So if you want to design, if you want to implement a continuous time filter, you'll have to convert it to a discrete time filter to implement it. And there are tools in Python for doing that. And then you can use the discrete time filter that's generated from that tool to implement your filter in Gridlab-D. All right, next is the schedule directive. So schedules are used to create recurring patterns. Recurring patterns in Gridlab-D. These are extremely useful for things like loads and tariffs and things like things that change in a regular pattern from minute to minute, hour to hour, day to day, so on. The POSIX standard allows you to specify the pattern down to the level of a minute and all the way up to the level of months. And it does allow weekday patterns. The parser understands commas and dashes so that you can describe, for example, this pattern in the first pattern in example here, 0 to 15 to 31:45 would make the first 15 minutes and the third 15 minutes of an hour have the value 0, and then the second and fourth quarter of the hour would have the value 1. Notice also that in the fourth quarter specification has a loop back, so that is allowed. You can notice that it goes from 46 to 0. What that means is essentially loop around and close the hour back to 0 with the value 1. The way you use a schedule is simply to take the name of the schedule and apply a linear transformation to it. And then that schedule is linked to the property, and the property will take the value that you have here through the linear transformation, and it will follow that pattern as the clock advances through the simulation. There are some options that you can apply to change how the schedule works. These are not used frequently, and mostly they're used to validate the schedule to ensure that it has characteristics that you need when it's loaded or when it's being applied to a property. So non-zero basically says the value in the schedule cannot be 0. And so that would, for example, make this particular example not work, because if it happens to have a 0 value, and it would then refuse to load it. Positive means that the values must not only be non-zero, but also non-negative. Boolean means that the value is to be interpreted as a true or false quantity. So non-zero values are essentially treated as true, and 0 values are treated as false. Normal, weighted, and absolute basically reinterpret the values and possibly scale them before applying them to the property. Normalization and weighting are done within a block, and so you can have actually multiple blocks, and I recommend you look at the documentation for schedules for how that's done. But then what would happen is that the values would be normalized within that block and scaled accordingly. Absolute basically means that the negative values would be made positive. Interpolation is used to fill in missing values. And so there are various mechanisms for interpolation. If you have a missing value, then that value will be filled in using, by default, a linear interpolation. I don't recall how quadratic is done or whether it's done, but basic interpolation allows you to deal with gaps in your schedule, if any. Next is the modify directive. This directive is used to take an existing object and change values after the object has been defined. So you can see here that we've defined a class test, and it has a property X. The units of the property happen to be defined in watts. And then we define an object of that class. We give it the name first, and we assign the property the value of 100 kilowatts. And then later we come along and we decide we want to modify that value. We use the modify directive to alter that value. This is particularly useful in cases where you load data from one source, but then you want to modify objects from a second source that might not be available to the first source. One thing I should note is only values are accepted here. You cannot do things like math and functionals and things like that the way you can in the object specification. The other thing is that the object has to have a name. You cannot refer to anonymous objects using this mechanism. Okay, the next directive is the script directive. This allows us to access external code and share data with that external code and allow that code to operate on, let's say, the model or various things externally. In this case, this example runs a shell script, and that shell script would then execute, and when it's done, the GLM file would continue processing. So you could use this, for example, to generate a GLM file that you then include, or generate a CSV file that you then use as an input to some object later on. This second example exports the global variable clock, which is the internal clock, and then runs on initialization. So notice that this is an event handler. So the script is only run during initialization, and it just echoes the clock value. And the output of that, of course, would be the initial value of the clock when the simulator starts. There are a number of event handlers that exist. OnCreate is used after the GLM file has been loaded, but before the simulation initializes. OnInit is run after initialization is completed. Pre-commit is run before a clock update occurs. Pre-sync, sync, and post-sync occur on top-down and bottom-up sweeps of the parent-child hierarchy when a clock update occurs, and that could happen multiple times. And the way it works is it basically continues happening until all objects report that they can move their clocks forward. Commit is called after all objects report that they can move the clock forward. And then term is called when the simulation is done and it begins the termination sequence, saving data and so on and so forth. So these event handlers can be used to handle all sorts of different things that you might want to do externally as the simulation advances in time. I just wanted to mention one thing. Exports only work for event handlers. They don't work for the main script. So now we're going to talk about macros. In general, macros are used to control how the Gridlab-D model is interpreted. So it controls the parser, essentially. The first macro is the macro that allows you to switch to a Python parser. And so when the loader encounters this string begin Python, it starts interpreting the content of the GLM file as Python code. And then when it encounters #end, it stops and switches back to standard Gridlab-D GLM parsing. And then, of course, as it does this, all the directives that you encounter in Python would be parsed and used. And in particular, you can use this Gridlab-D module to access the Gridlab-D model itself and the streams and such. So you can see how this sequence of printing information, depending on the stream it goes to, it might be blocked or displayed, and then using the Gridlab-D streams to output data. And later on, when we talk about programming in Python, we'll talk about this Gridlab-D module at great length. And we'll get into much more detail about how to work with the Python interpreter. But you can see the basic idea how this works and the various outputs that are generated as a result. Next, and probably one of the most important macros, is the define macro that's used to define global variables. And so here's an example of defining a new variable called test, and it just sets it to the value 1, 2, 3. You can define any existing value, and it will overwrite whatever was there before. You can even do it to the clock. That might not be the wisest thing to do, but it certainly is something that you can do. One thing that's important is that define will automatically create a value. The set macro will not. The set macro will respect the existence only of a value. You can suppress that behavior by using strict names. I'm sorry, this should say false. That's a typo. If you disable strict naming convention, then you can set values, and set essentially then behaves exactly like define. But the purpose is to ensure that you don't accidentally set something that doesn't exist. So as a general rule, unless you're absolutely certain you're meaning to define something new, set is probably a better macro to use to set global variables. Another important macro is the macro that allows you to download files from remote sources. This is done using URLs. You can use either wget or curl. One important thing to remember is that these macros only download the file and don't support any of the options that you would normally find with those commands. If you want to use those options, you should use the system macro to directly call the command itself, and then you can set the options you want, as is the case in this example, where you see a request to get the header information for a specific file. So this is just something to keep in mind, that these macros are not actually calling the function installed on your system, but just using an internal mechanism for retrieving files from the internet. The debug macro outputs debug messages if the debug option is turned on. And so here's an example where we enable debug and the message is displayed. And then when we disable it using the option command, it's no longer displayed. So only the one that we want is displayed. The other two are not. And so remember that the debug option on the command line is controlled by the option macro itself, and it's a toggle. If you want to set it to something, you should either set it to true or false according to whatever you want, rather than toggling it. Error works similarly, and when the loader encounters an error, it will stop processing and cause the loader to force the simulation to exit. And that's normal behavior. Errors are considered to lead to fatal errors at some point. And here the fatal error mechanism is to simply shut down command line parsing, which is in this case the loading of that GLM file. You can put whatever you want in the message. So there's no limitation of what you can put here, including global variable expansions and such. Those will be all handled as you want. The next macro is the for macro, which basically implements a for looping mechanism. That looping mechanism allows you to process, essentially set this global variable to each of the values in the list. And so you can see in this example, as it processes the command line of the for loop, this print command is executed with each of the values. So this allows you to repeatedly implement some operation with a value that goes through a list. One really important caveat with for loops is that the list has a limit of about 1,000 characters. And so if you return, from some external source, like a find or some value that you've read in, something that's longer than 1,000 characters, it won't work as expected. It'll just stop processing, or you might get a memory error. The only solution at this point that I know of is to break it up into multiple steps, or to do the operation during creation, an onCreate event handler in Python. And then you can usually do the same thing in Python that you can do in GLM. So my advice is to use these for lists that are short, and to resort to onCreate when you have very long lists. The Gridlab-D macro starts a new instance of Gridlab-D inside the existing instance. So the environment is kept the same, but it allows you to run it again. Here's a simple example. It just, runs another instance and reports the version of that instance. But you can use it to run variants of the existing model and for example, run the existing model with a new variable set to run an alternative scenario, for example. So that's the kind of thing that this can be used for. If def is a conditional block, allows you to test whether a particular condition is met and then conditionally load GLM code. So here's an example of a test to see whether a variable exists, and if it doesn't, to define it. And so that variable is then assured to be defined. Alternatively, you can test the variable explicitly and using an if test instead of a if def or if ndef. And in this case, it's a literal test. One of the options in the if syntax is whether that test is to be interpreted literally. So notice in this first case, the variable test is expanded. The difficulty with this is if the variable doesn't exist, that's not going to work correctly. It's going to result in a blank entry here. So this has the alternative of allowing you to test for the variable without having to do the expansion. But in order to do that, you have to set this literal if flag. This, by the way, is how the older versions of Gridlab-D worked. But this is now the default way newer versions of Gridlab-D, including HiPAS, work. The include macro allows you to include another GLM file and embed it into this existing GLM file. That's a fairly simple way of constructing large, complex GLM files from multiple files. It also allows you to use a couple of other alternative syntaxes. So, for example, if you use quotes, that includes a GLM file. If you use angle brackets, that'll include an H file, so a C header file that will then be used when compiling C code. We're not going to talk much about compiling embedded C code. It is a supported capability in GLM, but it's not one that's used very often, and we're not going to talk about it here. We'll talk about it later. A third capability for loading include files is to load a URL. And so that's just done with square brackets, and then you specify the full URL, and that GLM file will then be downloaded and embedded into the GLM loader's input, and it'll be included. There is an alternative syntax to include where you can specify the term using before you put the name of the file or the URL. And you can basically list some global variables that will be set while it's loading that file. So you can say using A equals 2, B equals 5. And then if you refer to A and B in the GLM file or in the downloaded file, they'll be expanded appropriately. And that allows you to basically create a list of includes with with variables that change from one include to another. So you can include the same house GLM file and change the phase on which the houses are attached, for example. Input is a macro that allows you to read data in from external sources. It almost always needs to know the semantics for the input and the output. And so that's what the -F and -T options for the from and to semantics. And then often you need to specify other information. And in this case, the most common is the module that's needed for that input to work if it's not specified in the semantics already. The class may also need to be specified, and you may want to specify specific properties. So here's an example of inputting a CSV file from the table semantics table and output to an object semantics. And you can see the CSV file specifies the class, the parent, the floor area. And what it's doing is it's specifying, it's creating objects called house and that belong to the parent main and have a square footage of 2,500 square feet. And so the result of this would be to create two houses on this meter that are 2,500 and 2,000 square feet, and basically connected to the meter. So this is the way that we can provide very large models as CSV files and create fairly complex models quite easily. Insert is similar to include. Essentially what it does, you can think of it as saying include, it's equivalent to saying include subtest.glm using test equals and then this value. What it's doing is it's essentially saying I'm expecting to find this GLM file by the name subtest. I'm going to load it with the global variable test set to this value. And so this allows us, in this case, to loop through the variable, the A variable set to 1, 2, and 3, and insert the file subtest.glm with the values test equals test 1, test 2, test 3. And oops, you can see it didn't work. I'm not sure why that happened. This should say test 1, 2, and 3. I'll look into that. Next is the on-exit macro. And so in this case, what happens is when the GLM file is loaded, if it succeeds, the exit code for the simulation should be 0. And if it fails, it will be some non-zero value greater than 0. So it could be 1, 2, 3, or 4, and there are, I think, up to, I don't know, I think up to 127 possible values. If you specify on exit -1, that just means that any non-zero value would be considered a reason to run this script. And then if you specify a specific exit code, it will run this script only on that specific exit code. This can be used to do all sorts of interesting things. Here's an example here where looping through the values, I can essentially execute the program again with the new value, and I can do this for each of the values up to 9. So the initial value of x is 0, and as long as x is less than 9, I keep running, and the simulation is successful, I keep running the simulation with the next value of x. And you can see then that the simulation runs with the value x equals 0, 1, 2, 3, all the way up to 9. And in this case, all it's doing is printing the value x, but you can imagine having running a bunch of scenarios this way for a series of simulations. You can also use this to check that the output was successful, and this is something that's very sort of standard in doing validation tests. On exit 0, look at the difference between the output file that I got and the output file that I expected. And if the two are the same, then the validation test passes. So that's a fairly typical way of doing things. The option command we already encountered and talked about earlier. It basically toggles any of the command line options that are available. Things like verbose, debug, anything which is just a switch on the command line to change a behavior corresponding to some true-false value. Setenv is used to set environment variables. Many shell scripts and other commands look at the environment, and that environment can be established using the setenv before you call a particular system command or shell command or anything which is a sub-process. These environment variables are stored in the process's environment, and so there are certain rules for the names and how they can be set. But for the most part, the standard text rules apply, and you should expect them to work as in the usual manner. The sleep macro is used to pause the simulation for a number of milliseconds. The purpose of this is to give the environment time to do something that needs to be executed. And so you might find this, for example, if you were to run a shell program that does something that takes some time, but you don't want to use a wait mechanism for doing that. Sleep is a perfectly okay way of having the loader pause before it resumes processing. So here in this example, it's printing the date, pausing for 5 seconds, and then printing the date again, and you can see that the time has elapsed accordingly. When sleep is not effective, and there are numerous cases where it may not be effective, either because you don't know how long you have to wait, or you don't want to wait sort of the safe time, a start wait mechanism is perfectly suitable. And so in this case, what's happening is that it starts an asynchronous process, and in this situation, it's just a file listing. And then it's waiting for that process to be done before continuing the loader. In this case, all ls does is it prints the local list of files, but that does take a moment to run, and it does have output. And so the wait command will wait for that listing to be completed, take the output, send it to standard out as expected, and then resume the loader after that's done. And so that's a very convenient way to do things like starting servers and anything where the time it takes to get go through the process and make sure everything is ready is unknown. There is a mechanism for the macros to process any of the subcommands that are available in Gridlab-D. This is a list of the subcommands that are available at this time. There will be others at some point in the future. But anytime you use the macro character, the hashtag followed by any of the subcommands, it simply executes the subcommand with all of the text that follows afterwards as the command line arguments. So here's an example of getting a list of all the weather in Wyoming. And so this runs the weather subcommand, retrieves an index of anything that starts with the characters WY, and that lists all the Wyoming TMY3 data that's available on the server. And so you can use this for a lot of different purposes, including generating plot files, doing matrix manipulations, retrieving libraries, running geodata. There's lots of things that you can do with these subcommands. And this just gives you an easy entry point for doing that. The system command allows you to execute code directly in a system shell. When you run the system command, it waits for the command to finish before continuing processing. So unlike the start command, which essentially fires and forgets, the system command will wait for the result to come back, send the standard output and standard error to your screen before continuing processing. And so you can see here's a system command that tells what system it's running on, and then executes the clock command to obtain the current clock value. Notice here that the clock value is expanded locally first before being passed to the system command. So this is not expanding the clock variable in the shell, it's expanding it in the GLM file. And so that's one important distinction from, say, the way the script command might work. Okay, next is the verbose command, which basically just enables, allows you to write a message out when the verbose option is enabled. If verbose is not enabled, the message won't be displayed. Verbose messages right now in Gridlab-D are always printed with this leading 3 dots. Gridlab-D is quite verbose when you turn on that verbose. This is what it prints generally when it has nothing to do, when you run it on an empty model. When you run it on a fully developed model, you could get thousands of lines of verbose output. And generally, verbose output is very helpful for figuring out why something isn't working the way you expect. Next is the version command. Typically, the version command is just used to check that the version is the one you expect. The simplest form of the command is just to check for the version number itself. And if it doesn't match, you'll get an error. But you can also check to see that it's greater than or equal or less than. Any of these are allowed, sort of the usual things that you might expect. And if you want details on this, you can look at the version subcommand or the version macro description in the documentation. One thing to note is when the version check fails, that results in failure of the simulation. So if it does not meet the requirements that you specify, the simulation will shut down. So be careful about using it, and specifically be careful about how you specify it, because you may be precluding runs that are actually okay in the future if you don't specify your version correctly. This would be a very restrictive test and would not work in the future, whereas version greater than equal 4.3 would work in the future without any difficulty. So that's just something to keep in mind. Warning allows you to print a warning message when warnings are enabled. And again, the option warning, if you use the pound option warning to disable warnings, then you won't see the message, but otherwise these warning messages are displayed whenever they're encountered. They don't affect the simulation itself, but generally it's a good idea whenever a user encounters a situation that is unexpected, where the result won't be something that you would normally expect. It's normal to put a warning message in the loader. So it's a good idea to include warnings when unexpected things occur that are not necessarily just errors. The write macro allows you to generate data from the model at any point in time during the loading process. Be careful, that is the model at the time it's encountered in the loading process. It's not the model at the end of the loading process. If you want to do that, you should use an on create or on init event to capture the state of the model after creation is completed or after initialization. But here's an example of a couple of test classes and test objects that are created and then written out to CSV for processing by some other portion of the system as necessary. So this is just a very simple way of taking the existing model data and generating it out in various formats. In the case where you need to specify information, generally right now it's a list of classes and properties, comma separated, and that list is then used to generate the CSV file. Okay. So now we're going to dive into some particulars about the semantics for various parts of the GLN syntax. And the first is collections. So there are a number of properties in Gridlab-D that actually take collections as their input. You encounter this, for example, with the collector objects in the tape module. And you can also encounter it with the find pseudo global, which we'll talk about later. Generally, it's simply a property, some kind of comparison operator, and a value. So, class equals test, or ID greater than 10, or something like that. Only invariant properties are allowed. So, as a general rule, properties that are defined in the class itself are considered to be variant properties, whereas header properties are generally regarded as invariant properties. As a general rule, it only allows you to compare and use properties that are considered to be fixed in the simulation and can't be changed over the course of the simulation. So output properties are usually not usable. Input properties of objects are. So here's an example of a couple of classes that are assigned, that are defined. And so you have class objects of test 1 class and object of test 2 class. And then here's a pseudo global find all the objects. Sorry, this is a typo. This should say test 1. Find all the objects of type test 1, find all the objects of type test 2, and print them. My apologies for the typo. I wasn't careful there. But you get the idea. Functionals are basically inputs to variables that are always going to generate a single double value. So a real value that's not a complex number, just a single real value. They can be implemented as math equations, as you see here in this first example, where the value v is simply x divided by t. They can be also schedules, as you see in this. Oops, I don't have a schedule example here, but we saw it earlier where an object was assigned the value of a schedule. And of course, they can be random numbers as we see here in these two examples with x and t being set to some random value. The equation technique is actually quite capable. So, for example, here we can see that it refers to the v value from another object with another name. So we can simply refer to an object name and its property and set that as well. In the case where we are doing a more sophisticated calculation, you'll notice that you can use the math equation and you can mix where the properties come from. So for example, it's taking here the value of x, squaring it, multiplying it by 3, and subtracting sine of the value of x from the first one and adding 2. And so that technique is supported for properties as they're being read in. This allows you to create properties that have sophisticated relationships with other properties in the model, provided those properties have already been defined. So that's one big caveat. If the property doesn't already exist, it cannot complete the calculation, and there's no such thing as postponing that calculation. Another interesting property is inherit. If you specify the keyword inherit, it will simply copy the property from the parent. This is especially useful when in power flow objects where you need to inherit the phases and the nominal voltage of the parent, and you don't want to have to set it all the time. That's a very convenient way of making sure that an object has inherited values that are the same as the value for the parent object. You can use JSON formatting for objects. So here, for example, is a complex value z. And of course, we can simply set the value of z using a complex number specification, or we can specify the parts. And what's interesting is that you don't have to specify the parts as literally the real imaginary parts. You can also specify them as magnitude or angle, or magnitude and argument, which is the angle in radians. And you can even do some oddball things like specifying a negative magnitude with an angle 0, which would be the same as a positive magnitude with angle 180. And so this ability to use the features of an object to set its properties is quite helpful. And many complex object property types like end uses, load shapes, and such allow you to do this, to set the, basically to create the property with the correct features that you want. I mentioned earlier random variables and the distinction between the functional random and the random variable itself. And so now I'm going to spend a little bit of time talking about how random variables work and how they're set up. So a random variable is a variable that changes during the course of the simulation according to the specifications that you provide. Here's an example of a random variable with the type normal, with the mean 0 and standard deviation 1, so it's truly normal. But it's clipped at the values -3 and +3. So essentially any value beyond outside 3 sigmas will be truncated to negative or +3. And the variable is updated every 60 seconds. So this refresh statement allows us to tell the simulator to update the random variable and essentially resample the normal distribution every 60 seconds. That allows us to create a kind of noise in the simulator, but determine the frequency at which the noise occurs and perhaps clip the noise truncated essentially at values if we want. A lot of different distributions are supported, and we'll talk about all of the available distributions in a minute. You know, the common ones are normal, uniform, things like that. Another one that's used often is triangle, which is essentially similar to two linear ones with a midpoint, and you can specify then the range between the two, and the height of the triangle distribution is based on the idea that within that range the sampling is unitary. So it gives you a 1.0 probability of sampling within that range. Another thing that's important and very useful is the ability to set the correlation. So if you specify correlation with another property, then the random variable will be based on essentially a weighted contribution from that other property. So in this case, it's correlated to with a correlation factor of negative 0.9 times that other object property X. So in this case, it's the same object, but it's this property, the random variable generated by this property. And what that gives you essentially is two random variables that are normally distributed that have a strong negative correlation with each other. And so you can use this to define a cascade of correlations and create multi-dimensional random distributions that are, that have correlations with each other. And then when you run the simulation, you see the output. You would not be able to tell there's a correlation until you had a very large number of samples, but I think you can see the trend here. Notice that these values are all positive and these values are all negative, and they are rather similar to each other when they come out, indicating the strength of that correlation. And so that's a very useful mechanism for generating multidimensional random variables. Okay, now we're going to get into some of the more difficult to use but very powerful syntactical features of the Gridlab-D properties. There is a syntax called delayed expansion, which uses the backticks. And the idea here is that some properties should not be expanded when they're first encountered, but rather should be expanded as late as possible during the generation of the value that's going to be stored. And in this case, we need to wait until the object is completely defined in order to know its class and its ID, so that we can generate the name of the object based on the class and ID. And this will become very true when we're doing looped objects and for loops. So notice here that this object is implicitly looped, it's repeated. And so this syntax allows me to create 5 example objects from a single entry, but I don't want these IDs to be the same in each object. The class is always the same, but the ID is different. And so this delayed resolution allows me to capture the ID number in the name without having to use, say, the math expansion of ID, which would not work correctly because it's generated before the object is created. So this gives me delayed resolution of these properties. There are a lot of different properties that have delayed resolution. The header properties themselves, class ID, group ID, rank, latitude, longitude, the state of the random number generator, and what's called the global unique ID. This is an ID that is guaranteed to be globally unique. It's just a big number, but it's a number that's so large that it's like age of the universe, unlikely to repeat. And then finally, there are a number of special properties that you can use as well that are taken from the system that may not be normally available, but can be available on this kind of delayed resolution. The name of the file, the path name to the file, the actual file name, what some people call the base name, the extension of the file or the file type, namespace, which is not an important thing to know about. Host name and host address are the name and IP address of the computer you're running on. I forget what CPU is. Oh, it's the processor ID for the thread. Process ID for the whole process itself, which is something you use if you want to guarantee your program is using a unique file name. And port number is the port used to talk to the Gridlab-D server when it's running. So these are just special things that you may need to have access to. Otherwise, generally, when we expand global variables in properties, we have access to a number of expressions and expansion syntax. The first is the sequence syntax. So any global variable that starts with seq underscore can be defined as an automatic sequence numbering system. You can initialize a sequence, basically reset it to 0 with the syntax sequence _x : init. And then you can increment the sequence using the :inc. Either case, it returns the value. And of course, if you leave them out, it just returns the current value of the sequence number. So we use this a lot when we're generating ID numbers or unique numbers that we need in a row, for example, file names for meters and things like that. That's pretty common to use this mechanism. The other mechanism that's available is expressions. And there are a lot of different expression syntax available. These are they're patterned off of shell variable expressions. And so they basically mean different things. Like this one, the second one means use the default value if the name is not defined. And so they all have different meanings. And I'm not going to go into these in great detail. I'll refer you to the shell syntax or the documentation Gridlab-D. But some have great usefulness. So this one, for example, will clip the string at the offset. This next one will clip the string at the offset with the length. You can do pattern substitutions. The / is a repeated pattern substitution. And then there are a bunch of math operations that you can do as well as ternary value evaluation, which is similar to what we saw before, where it tests the name and then returns either a yes or a no value. So these are quite powerful and can be used in a lot of different ways. And I'll refer you to the documentation for details on how to use all of those. All right, so now we get to what are called pseudo globals. So these are global variables that are not actually variables. You can think of them as functions, but they perform some very useful operations. So for example, the global variable file name can be given a path, and it will extract just the file name portion of the path, in this case, name. File path will extract the directory of the full path, and file type will extract the extension of the full path. So these can be useful to take apart file names when you need to, for example, do substitutions or take a file name, replace its extension, things like that. The find pseudo global searches the objects in the model and finds all the objects that meet a certain criteria. We talked about the collection search criteria earlier, and that's definitely a case where this is useful. So for example, you can find all the objects of a class, and it will return a string that contains all the classes that meet that object naming constraint. So there are a lot of different search features available. If you happen to need a new search feature, you could certainly put in a request. Every once in a while, people come up with a new need, and it's relatively straightforward for us to satisfy those, but we've included most of the ones that you would want, which is searching on different property criteria. Find file is a pseudo global that looks for a file that matches a pattern in the search path for Gridlab-D. You can alter that search path if you want. It's the global variable GL path. Actually, I think it's the environment variable GL path. But find file searches in that path for whatever pattern you are looking for. Geocode does a lot of geographic manipulation. It primarily is designed to convert latitude and longitude to what's called a geohash. A geohash is a unique coding mechanism for a location that allows you to do searches for things like proximity of one location to another. It has a resolution associated with it, so you can geohash latitude and longitude to different resolutions. It's a number of 1 through whatever. I think the limit is practically somewhere around 10 or 12. And there's a table for knowing what the resolution corresponds to in terms of distance. If you give the name of an object, it will look at that object's latitude and longitude and then convert it to a geohash at that resolution. And of course, if you give it a geohash, it'll do the reverse. it'll convert it back to latitude and longitude for you. So geocode is a very useful one for anybody working with geodata. Next is the Python, which simply executes the Python command and takes the standard output and returns that. So very useful for doing quick Python commands and operations that you would otherwise find rather difficult to do in the Python syntax itself using begin, end, or a shell script. The range pseudo-global just returns a series of numbers in a range. The first character after the range word is the separator. So generally people use spaces as the delimiter. So you would say range space, start, comma, stop, comma, step, and then it would return a list of numbers from start to stop, stepping by the number that you specify. But if you say, for example, range, comma, start, comma, stop, then it would separate those numbers with commas instead of spaces. You could use colons, slashes, whatever it is that you want. So that's very useful as the list generator for a for loop, for example, but it can also be used in a variety of other ways according to whatever it is that you're trying to do. Finally, the shell command takes the output to a shell and embeds it. So you could, for example, take the list of files and apply it to a for loop, and you would get a for loop over the list of files just using shell ls, for example. Finally, there's a special property in some objects called a method. So we've talked about generally up to this point properties that actually correspond to things like complex values or double values or strings. Methods work a little bit different in that they accept inputs with the purpose of changing the behavior or passing information to the object that the object will then handle. And then if you were to call and ask the method object for a value, it would return information about the object associated with that particular method. So here's an example. The recorder object uses a method called property to allow you to list which properties you want. This allows you to provide a nearly unlimited list of properties, so you don't have the 1024 character limit on the input value. And so here you see, for example, property X and property Y are provided separately to the method, and when you output the data, you can see that both X and Y are listed. If you were to ask the recorder object for its list of properties, it would return both X and Y. It would tell you that it has both properties as its input. And if you were to pass X comma Y to the property method, it would work similarly. So this allows you to deal with objects that have much more complex behaviors than you normally encounter if you were to simply provide inputs as a text string. This is going to become much more commonly used in Gridlab-D for rich behaviors, but right now it's used primarily by the tape module. The next important thing to use in objects are event. So this is how you create an object event handler. So here we have a module that we've loaded. It's a Python module. We define a class in that module. A class in this model that implements a double of type X, and we're just generating a random number for that. But we'd like to call the event handler for this commit event handler, and it will call a function called myInit. I should have called it myCommit. In fact, I will fix that at some point. It doesn't matter. But you can see that in the Python file itself, I have two event handlers. One called onInit. That event handler is called when the module is loaded. So when the module is loaded and we initialize Gridlab-D, it will call this init handler. This function, myInit, is called whenever a commit event occurs in the object itself. So notice here, that on init is called when the initialization of the simulation occurs, but this second myinit is called when the commit handler occurs. So we can use this to create all sorts of event handlers for different events in objects, and those objects will then call these Python code fragments handlers when appropriate. Each event handler has some requirements about what is returned, and I'll refer you to the documentation for the Python module itself for the details on this. There's quite extensive documentation on how to do this, and it's not something that we have time to cover in today's session. We'll talk about it later. All right, the last thing I'm going to cover in today's session is the JSON semantics itself. When Gridlab-D outputs a JSON file, that JSON file has a pretty standard set of objects that it includes. So it's a dictionary, and that dictionary has some keys that are always included, others that are only included sometimes. You will always find the application and version keys are included, and you will almost always find modules, types, header, classes, global, schedules, and objects are included. There are others that may show up like filters, depending on whether the model includes those things, but they are now not required to be in the model. So the application element is always going to be the word Gridlab-D. That's how we know that we've got a Gridlab-D JSON file itself, and that we expect to find these other components. The version number will be essentially the version that created this JSON file. So it can be, if it's an older version of Gridlab-D, it will have an older version number than the current version you may be using. That doesn't mean it's not compatible, but it does indicate that there may be pieces missing or things that might be defined differently. And so it would be important to pay attention to the other information that's provided in the modules, data types, header, classes, and global variables to ensure that the older version is modified or updated correctly to guarantee that the values correspond to what's expected for the current version. The schedule and object definitions will be the actual model itself, whereas everything else will be the metadata that is needed to interpret the model. And so we'll go over all of these now and talk about each of the metadata and then the model data itself. So as I said, the version is generally the version that you're currently using, unless you're loading an older file. If you need to get the parts, you can either split this up when you're processing it. That's major, minor, and build, or you can just go to the global variables and ask and inquire the global variables version.major, version.minor, and version.patch. You can also use the global variables to identify the branch and the build, as well as the platform on which it was the file was created. As a general rule, these things should not matter, but every once in a while, it's something that is used particularly for validation and testing or for diagnostics. The modules themselves really just list the module that's loaded in the model and the version that's loaded for that module. Right now, it's a rule that the major and minor of the modules should match the major and minor of the version itself in Gridlab-D, so that you would expect the major value and the minor value to be the same as the major minor for the version itself right here. I'm not aware of cases where that would not be true, but it's just something that we can use for validation. At this point, there's nothing else in the modules key itself that we are particularly concerned with, other than just knowing which modules are loaded in the model. That will tell us which classes are available, and it will tell us what globals have been defined by the module and what behaviors we would expect to see from classes in those modules. The JSON types key is used to describe the properties of the various objects that are implemented. The various properties that are implemented in objects in Gridlab-D. This is useful for basically to know how to interpret and manipulate various object types, and in particular knowing, for example, what the XSD types are, or whether there's a string converter available, and so on and so forth. So this is basically all related to the internal behaviors of Gridlab-D data types and what we would expect to find in the system when we're trying to use these data types. So as a general rule, programmers aren't going to need to know this. The API needs this information, but as a programmer, you generally don't need this information unless you're doing some very esoteric things. The header key contains all information that's related to the header properties that are included in every object. As a general rule, the headers, the data is protected, but not all of them are. For example, latitude and longitude are not protected. So this just tells you what the data type is internally and whether access to the data type is limited. This would, for the API, this is useful for knowing how to translate the data that it's getting. Next is a list of all the classes that are implemented by the modules and or defined by users. There's some information related to the classes usage that would be output if the JSON file was saved at the end of a simulation. So we would know, for example, how many objects were defined, how much time the class took in processing. But the important things are what module does the class belong to, and what properties does it implement, and what are the characteristics of those properties? What data type does it have? Is it accessible? Is it a required property? Is it an output? Is it an input? That kind of thing in the description. So all this information allows an API to help the user access the property and define defaults and things like that. So all of this information is can be provided in this enumeration of the properties of a class. All the globals are listed. It's a similar type of thing. Each global is provided, its type, the way, how it's accessed, the current value of the global. If it has keywords associated with it, the values associated with each keyword are enumerated as well to allow an API to know what's permissible and what's not permissible. There are, I think, nearly 100 globals. I don't know. There's a very long list of globals, and those are all available in the documentation. As a general rule, not only will all the globals defined by the simulator be listed, but all the globals associated with each module, they will be listed as well, and each global that the user has defined will also be listed. So that's quite a long list, but you have access to everything through this global keyword. Schedules are basically written out as they are found in the model. So the original schedule definition is stored. The schedule is not expanded into the full calendar. The way schedules are expanded, you end up with 14 calendars, one for each of the year that you can find. There are 7 years that exist, 7 calendars that exist for non-leap years, and 7 calendars that exist for leap years. So there's a total of 14. The expansion for those can be obtained from Gridlab-D through debugging, but it's not something that is shared in this schedule mechanism itself. And so what you see here is the original specification. So when Gridlab-D JSON file retrieves a schedule, that's what it sees. It's just the original spec. And then finally, all the objects are enumerated. They are listed by their object name. And then all the information related to the object, including all the header information, as well as all the properties of its parent classes and the class itself are included. So everything is listed. All the values are given as strings. so that they can be interpreted by the program that reads them in a consistent manner. So for example, notice here that the violation rating, which we know is a double internally, but it has units of amps. So you'll see here that the violation rating is 0 amps. And so the unit is included. That's very important for ensuring that values that move between one class and another, or one program and another, are provided in a way that protects the units and ensures correct conversion. So that's basically all of the objects that you find in a model. The last key type that's not always in a model, but will be found in there if filters are used, is the filter keyword. Basically, they're listed by the name of the filter. So here's my delay filter from earlier. The domain is given. The time step, this is how often the filter updates. Time skew is an offset on that update, so that you can, in fact, cause it to not only update every 5 minutes, but with an offset of, say, 10 seconds or 30 seconds with respect to that 5-minute update. And then the numerator and denominator, and then other information that might be associated with it, such as the min, the max, and so on, resolution. So okay, so that is pretty much it for what we've got in today's session. And so I'll open it up for questions for all of you. Feel free to ask your questions. You can post them in the chat, or simply unmute yourself and go ahead and ask your question. This is the exercise for next week. Basically, to create a simulation that runs from midnight January 1st, 2022 to February 1st in Los Angeles, with a schedule 9 to 5 weekdays at 1, 9 to 5 Saturdays at 0.5, and just implement a class with the value X coming from that schedule and a value Y that is a 1-minute delay of the value X, and record the changes in a CSV file. So this should be a fairly straightforward exercise, and I will give you the solution to that exercise next week. Okay, so open it up for questions.
Yeah, Dave, good morning. Used, or when filters are used?
Anthony, you were breaking up really bad there, so I wasn't able to catch what you said.
Okay, can you hear me okay now?
Yes.
Could you provide an example of how filters are used or when?
Sure. So let's suppose that you have an object whose behavior is known to be like a second order transfer function in continuous time domain. Let's say it's a mass. I'm going to give a physics example, but a pendulum type. Oh, I'm sorry, a spring mass, right? And so it has mass and inertia, and so you would have a second order transfer function that would characterize the response of your system, that particular system. And so let's say X is the position of that mass, and then your input to that transfer function would be an impulse on that mass, right? And so you don't want to develop the full model in Gridlab-D of that spring-loaded mass response, but you know that it can be represented with this continuous time transfer function. Then you can convert that to a discrete time transfer function with a time step that's appropriate for the behavior of that mass. Let's say a 1 second time step. It would have to be a fairly big mass for a 1 second to work like that. But and then you can model that behavior without developing a full class, right? You could take the input, which is the impulse, and the output, which is the position, and get a class to represent that response. So you could, for example, approximate a house behavior with that. It'd be very approximate, but it's convenient because it's extremely fast. The performance of a filter is far superior to the performance of a full class that implements all of the behaviors. So that's one example of how you might use it. You could also use it to do just a first order difference of a value. Let's say you've got data that's energy data, and you want to get power from that energy data, or average energy over a fixed time interval. First order difference transfer function would do that. And then a real common one, which I used in an example, is a delay. Any other questions?
Dave, I have one question.
Yeah.
So for the inherit the property, so you have, if your example is you have a child object which is coded inside a parent object, right? So if I have an object which is coded separately outside the parent object, but I name as a parent refer to some object, can I use the inherit to define some property?
No, it doesn't work. At that point, you would have to use the name of the property instead. You would just, well, I think there's an example of that. Let me see if I can find it again. So here's an example. I mean, it's not, let's see, name second. So yeah, this is how you would simply refer to another object. So the fact that it's a parent object doesn't matter. You just use its name. That's how you refer to a value directly. So if you have the name of the parent, then you already know. That makes sense?
No, I refer to the page. There's a page I can use the inherited. There's one like and this one. So
yeah. So
this for this child. Yeah.
Go ahead.
Okay, so for this there's a child object, right? Object test inside the parent one. So for the X, you put inherit, so you can inherit the property the value of the parent. But can I declare this child object outside the parent one, and then I identify the parents to be that one, and then I use inherit?
No.
Can I do it in that way?
It doesn't work. No, it only works on nested objects.
Okay, I see.
Yeah, I'm pretty sure.
That's my question.
Yeah, it does not work otherwise.
Okay, so be embedded.
Yep, only when it's embedded.
Okay.
Any other questions? All right. Oops, I don't want to show you that yet. Okay, very good. Well, thank you, everybody. And we will resume again next week at the same time for session 4, where we will be talking about testing and validation procedures and how to create validation tests in Gridlab-D. Until then, have a good week, everybody. Thank you.
Thank you. Bye.